This is 12.3.1, the Michelson Morley experiment. Which is also called the interferometer. So Michelson and Morley set out to do an experiment in order to try to prove a hypothesis that there was something called absolute motion. So what they proposed was that there's this thing called the ether that just sort of exists in the background of reality, and light travels through this thing called the ether. So their proposition suggested that because light travels through the ether, and the Earth is moving within space. So as the Earth moves within space, the Earth itself is moving within the ether. Or, from our frame of reference, because we don't notice the Earth's movement, it's like the ether is moving over us, right? It's kind of like if you think of magnets and magnetic fields, either you can move the magnet and the magnetic field moves with it, or you could move a coil in the magnetic field and it has the same effect. So this ether is kind of like moving over us because we're moving in space on the Earth, and so that affects the motion of light within space. So to do this experiment, what they set up was a turntable which allowed them to rotate the experiment, and they started with a light source. And then they put two mirrors, one there, one there. And then they put a semi-reflective mirror in the middle. So this is a semi-reflective mirror. Which means that it can reflect some light, but it can also allow some light to pass through. So when the light source is switched on, ray of light comes out of the light source to the semi-reflective mirror. Some of that light is reflected upwards and some light is transmitted through. Then at each mirror, light is reflected. The light from the top mirror comes back down and transmits through. We'll put a screen on the end here. Passes through the semi-reflective mirror. And the light from the right-hand mirror is reflected back and then is reflected down by the semi-reflective mirror. So, what's happened here is both of those rays moved by some path, and then they met back at the screen, where they recombined, or at the semi-reflective mirror, where they recombined and then created a pattern on the screen. So an interference pattern, for example. If both of those mirrors were set to be the same distance apart, then we expect the path difference to be 0 lambda, or an n lambda, and so the pattern that we get will be constructive, or we'll get some pattern basically on that screen. Now we introduce the concept of the ether. So I'm going to draw the ether in a different color in the background. So these blue lines are the ether. And you notice the ether has a certain direction towards the left. So think about it as some sort of river or water that light travels through. Some sort of medium that exists everywhere. And because we're moving in space, the ether is moving relative to a certain direction. So that's towards the left. So the ether is, and I'll put in comma, blowing like wind. Which means that as we're moving, this ether is affecting light in a certain way. Now, if the ether is blowing like wind on light, because light travels through the ether, if we then rotate this experiment, then the relative direction of the ether to the positions of light changes. So as that happens, if we rotated the experiment around, the rays of light will be affected in different ways. For example, if the ether is blowing to the left or moving towards the left, then that means that it causes the path difference of light to change depending on how we rotate the experiment. And if the path difference changes, that means the pattern that we see on the screen should have changed. So for example, the light that's going vertically in this instance is being blown by the ether, but is still moving vertically up and back down. So the vertical light should be, in essence, moving faster or doing a longer path than the light that's just moving along the ether. So going horizontally, moving in the opposite direction to the ether, it has to move faster along the ether compared to when it's coming back, because the ether helps it along the way coming back. So rotating the experiment should have resulted in a change in the pattern seen on the screen. But they observed no difference. So if there was ether, the path difference should have changed when the experiment was rotated by 90 degrees. However, the pattern did not change. Which meant that there was no such thing as ether that was affecting or influencing the light. So, if the pattern didn't change, then regardless of the frame of reference or where we positioned the light source or how the light source emitted, the speed of light did not change. And this is something that will come up again in the next module, or topic I should say, which is that the speed of light is invariant. Meaning that no matter where you observe it from, how you observe it, what frame of reference you're looking at light from, the speed of light will always be measured as 3 times 10 to the 8. Including something that's quite strange, which is that if you're on a train that's moving at 90% the speed of light, if you were to shine light on that train and you measure the speed of light, you wouldn't measure it as 10% of the speed of light, you would still measure it as the speed of light. So we say that the speed of light is invariant. So this means that speed of light does not depend on the motion of the observer. It is the same in all frames of references, or in all frames of reference. That's the end of 12.3.1.